All right, hey everyone. So today we are going to be talking about concavity and points of inflection. Okay. So first off, I just want to start today with a little bit of a reminder, okay, that when we use the first derivative, this can tell us a few things. This can tell us where a function is increasing and decreasing. It can also give us any max or min values, which are known as extrema. Okay. What we're going to be doing today, which is going to be from the second derivative, this is going to tell us about a function being what we call concave up and concave down, which I'll explain what those both are in a second, as well as the point of inflection. Okay, so let's get into this new stuff here, this concave up and concave down idea. Now, let's start by looking at the graph of y equals x squared. Okay, the graph of y equals x squared looks something like this. Or, I'm going to say x squared plus 1, just so that we raise it 1 here. Okay, so this looks like that. Now, what I'm going to do is I'm going to estimate what the slopes of the tangent lines look like here. So like if I drew in this tangent line, the slope of that maybe is like -4. If I draw in the slope of the next tangent line, that's like -2. Then here, this is a slope of 0. The slope of the tangent line here, maybe that's a +2. And the slope of the tangent line here, I don't know, maybe that's 4. I'm just kind of estimating this right now. But notice your slopes go -4, -2, 0, 2, and then 4. The slopes are increasing. When your slopes of your tangent lines are increasing, this is what we call concave up. Okay, and a good way to think of concave up is to think of this as a smiley face. Okay, if your function looks like a smiley face or any part of a smiley face, you have concave up. Now there is like a full definition that we can kind of write at this. It says if f is a differentiable, or if f is differentiable on an open interval, then it's concave up if its tangent lines have increasing slopes. So maybe we should just kind of jot that down. So concave up. If f is a differentiable, or I should say is differentiable on an open interval, then it is concave up. Concave up. If its tangent lines have increasing slopes. If its tangent lines have increasing slopes on that interval. So as you can see here, okay, our slopes increase from -4 to +4. Well, guess what? I bet you can figure out what concave down is here then. Okay, so let's take a look at what if we had y equals -x squared plus 1. So let's take a look at what this graph looks like. So we're going to go to +1 here, but this is going to be facing downward here. So if we were to kind of look at these slopes now, okay, this slope is like maybe 4, then maybe like 2, then 0 slope, then it's like a -2, it's going downward, and then this tangent line is maybe a slope of -4. Okay, this goes from 4 to 2 to 0 to -2 to -4. It's getting smaller and smaller and smaller. So we say a function is concave down, which I can write as a frowny face. Okay. We say if f is differentiable on an open interval, then it is concave down if its tangent lines have decreasing slopes on that interval. Okay. And also for like concave up and concave down, like when you're thinking about this, it doesn't have to form a perfect U. It could be any part of your smiley face. So like in order to be concave up, okay, this is considered to be concave up still. Or you could have the left side, okay, if you just had this is still concave up here, okay. Same thing for concave down, okay. If you have any part of it, that's concave down. So this is still concave down, this function right here, okay. If you had the right side anywhere, okay, so say you have this, that's concave down still. It's the right side of a frowny face. It's the left side of a frowny face, and so forth and so forth. Okay, so that's what it means for a function to be concave up and concave down. Let's talk about then also the point of inflection. Okay, so point of inflection. And I'm just going to put it in very general terms here. A point of inflection is where a function changes concavity. So either it goes from concave up to concave down, or it goes from concave down to concave up. An easy example of this is, let's look at the graph here, y equals x cubed, let's just say x cubed plus 1. Okay. If I'm looking at the graph x cubed plus 1, it's going to look like something like this. It goes through the point 0, 1, and before it, it looks like this, and then it goes up like that. So if you'll notice here, let me kind of trace this. Okay. This left-hand side here that I'm highlighting in yellow, okay, do you think that's concave up, or do you think that's concave down? Okay, well this is part of that frowny face. It's the left side of a frowny face. So this right here would be concave down. Then what you'll notice about the right-hand side, okay, okay, if we notice the right-hand side here, notice that's the right side of a smiley face. So if that's the right-hand side of a smiley face, that's going to be concave up. So it switched from concave down to concave up. So the point that where it switches right here, this point, that 0, 1, that is my point of inflection, because it switched from concave down to concave up. So it has to switch from one to the other, either from down to up or from up to down. Okay. And so here's what I want to just note. Use the second derivative test. Second derivative test to determine concavity and points of inflection. Concavity and points of inflection. Okay, so what I want to do now is let's take a look at an actual example here, and we're going to show how we're going to do this. So example. Let's say we had y was equal to x cubed over 3 minus x squared minus 8x. Okay. And the question said, determine where the function is A, concave down, well, I'll start with down, concave down, B, concave up, where the function is concave down, where it's concave up, C, determine where the function is, well, let's just start there. Okay, A and B, perfect. Okay, so what we want to do is we want to do the second derivative test. So in order to do that, we're going to have to start by getting what the first derivative is. Okay, so we're going to use our derivative here. So we're going to do the power rule. Bring your 3 down in front. So that's going to become 3x squared over 3 minus 2x minus 8. Now 3x squared over 3, that's just going to become x squared. So my derivative is x squared minus 2x minus 8. Okay, so then let's do the second derivative. So second derivative, we're just going to take the derivative of this again. Okay, so if we take the derivative of this again here, derivative of x squared becomes 2x. Minus the derivative of 2x is just 2. And derivative of negative 8, derivative constant is just 0. So that's just going to disappear there. Okay, so now, just like we did with the first derivative test, okay, second derivative test, once you have your second derivative, we set it equal to 0. So we're going to solve for when 2x minus 2 equals 0. So I'm going to simply add 2 to both sides. And we get 2 is equal to 2x. And then simply just divide by 2. And that would give us that x is equal to 1. Okay, so let's do the second derivative test. Second derivative test. So we're going to go ahead and make our number line. And we put our point on there, which is x equals 1. Okay. And now we're going to test out values around that point in our second derivative. So I'm going to choose the point x equals 0 to the left. And let's just choose x is 2 to the right. Okay, here's my second derivative. If I put in x is 0 to that, we'd get 2 times 0 minus 2. 2 times 0 is 0. 0 minus 2 is negative 2. So this would be a negative value. Then we're going to put in x is 2. So 2 times 2 minus 2. 2 times 2 would be 4. 4 minus 2 is a positive 2. So this is going to be positive here. Okay, now which one do you think is concave down? Okay, well, concave down is going to be where your second derivative is negative. So concave down is where the second derivative second derivative is negative. And then you can probably guess that concave up is going to be where the second derivative is positive. So the second derivative is positive. So here, our function is going to be concave down where it's negative, which is right here. That goes from negative infinity until 1. And then it's going to be concave up where it's positive. Okay, so that's going to be negative, positive. Okay, and that happens from 1 until we reach positive infinity on this end. Okay, now, see here, let's just say it had said find any points of inflection, which is commonly abbreviated as POI. Okay, well, we would say to ourselves, well, do we have a point of inflection here? Well, a point of inflection happens whenever you switch concavities. And here you can see it goes from concave down to concave up. So that means at x equals 1, we have a point of inflection. So it occurs at the point 1, comma, okay, and this is a point of inflection. So I want the point, an x and a y value. Well, to get the y value, I have to go back to the y equation. So I'm going to put 1 back into my y equation. So it'd be 1 cubed over 3 minus 1 squared minus 8 times 1. So that would be 1/3 minus 1 minus 8, which would be y equals 1/3 minus 9. 9 is the same thing as 27 over 3, so that's like 1/3 minus 27 over 3, which would be negative 26 over 3. Okay, so our point is 1 and then negative 26 over 3. Okay, and that would be all of our information there. Now, let's just show this and let's see what the graph actually looks like here. So let me pull up a program we can graph this in. Okay, so our equation there was y equals x cubed over 3 minus x squared minus 8x. So I just want to show you kind of what this looks like here. Okay, let's make this a little bigger. And why don't we squeeze this down so it fits in here. Oops, almost. Okay, that looks pretty good. Okay, so we set at 1 and then that point negative 26 over 3, whatever that is. Negative 26 over 3, which is negative 8.6 roughly. So there's my point of inflection. And now you'll notice what happened on the original curve here. Okay, on our original curve, it started that this was going and it was concave down until it hit our point of inflection there at 1. After that, it switched to concave up. So this is a frowny face, concave down. And then after 1, it was a smiley face. So that was concave up. And that's exactly what we determined here when we did that out. Okay, so that's all we're looking for, something like this. Okay, so that's how you're going to go ahead and determine concavity and all of that stuff. I don't know why this didn't close. Let me close this program. Okay, interesting. It looks like it's frozen on there. I don't know if you're seeing this on your screen. Oh, there we go. Exit drawing. Okay, perfect. Okay, so here we go. So that's how we're going to be doing these, determining where it's concave down, concave up, and whatnot. All right, let's take a look at a second example here. So example number 2. Okay. So for this one, it says given. Okay. So given f of x is equal to x to the 4th minus 6x squared, determine all intervals on which f is both, or actually let's just say on where it is concave down. Okay, so again, just want to remember that concavity comes from that second derivative. So we have to get this down to the second derivative here. So our function is x to the fourth minus 6x squared. So let's go ahead and take the derivative of that. So we get f prime of x is equal to, and this would be 4x cubed minus 12x. And then we're going to do the second derivative of that, okay, which would be 12x squared minus 12. So now all we want to do is we want to just go ahead and solve for when that equals 0. Now, why don't we go ahead and first factor that down a little bit more. So I notice that I can pull out a 12 from this, which would leave me with x squared minus 1 on the inside. Okay, and now we can go ahead and solve this. If you want, you could factor that down a little bit further. So some people like to factor this, or you could just tee it off right here. But x squared minus 1 can factor to x minus 1, x plus 1. That's using that difference of two squares there. And so then if we set that equal to 0, we're going to go ahead and tee it off and set everything equal to 0. Okay, so here we have x plus 1 is equal to 0. Here we're going to have that x minus 1 is equal to 0. Definitely we could tee this off too, but again, 12 doesn't equal 0, so we're just going to ignore that part. We can basically divide it over to the other side. And here we'll get that x is equal to 1 and x is equal to a negative 1. So once you get that, we're going to do our second derivative test. The second derivative test is going to determine our concavity. So we are going to put our points where it equals 0 onto our number line here. And we're going to test out some values around those points. So why don't I use in between, I'll say 0. To the right, I'll use 2. And to the left, I'm going to use negative 2. Okay, so let's go ahead and try these out here. Okay, so let's start with negative 2. So we're going to do f double prime of negative 2. Now, I'm going to use the fully, actually, you know what, it'd probably be a little bit easier to use this one right here. Okay, you can use any second derivative equation you want, doesn't matter. I'm going to choose this one for this. So we get 12 times negative 2 squared minus 1. Well, negative 2 squared is 4. 4 minus 1 is 3. And then we have 12 times 3, which is 36. So that's going to be positive here. Okay, then let's do 0. So f double prime of 0. I'm going to use the top equation for that one, because that's just 12 times 0 squared minus 12. 0 times anything is 0. Minus 12 would be negative 12. So this is going to be negative here. And then we're going to do f double prime, the second derivative, at 2. And again, I'm going to use that top equation here for this one. We had 12. Sorry, not the top equation. Let's use this equation. So we're going to 12 times 2 squared minus 1. 2 squared is 4. 4 minus 1 is 3. So again, that's 12 times 3. Or 36. So that's a positive value. So again, what you want to remember is when you do the second derivative test out here for this, okay, where the second derivative is positive, that tells us where the function is concave up. Where it's negative, that tells us where the function f is concave down. And then over here, obviously, this would be concave up. So we want to know all the intervals on which f is concave down. Well, you could see it's down, concave down. Okay, on the interval from -1 to 1. And delta math uses parentheses for this. So we're going to use parentheses -1 to 1. So rather than the brackets for this, make sure you use the parentheses for concavity. Okay, concave up and concave down. And there you go. And that would be the answer to this problem. So there's a few problems on delta math now that I would like you to go ahead and try out. And let's see how you do with them.